The hydrogen economy is a proposed system of delivering energy using hydrogen. The term hydrogen economy was coined by John Bockris during a talk he gave in 1970 at General Motors Technical Center. The concept was proposed earlier by geneticist J.B.S. Haldane. Proponents of a hydrogen economy advocate hydrogen as a potential fuel for motive power and onboard auxiliary power, stationary power generation, and as an energy storage medium. Molecular hydrogen of the sort that can be used as a fuel does not occur naturally in convenient reservoirs. Nonetheless, it can be generated by steam, reformation of hydrocarbons, water electrolysis, or by other methods. The spike in attention for the concept during the 2000s has been repeatedly described as a hype by critics, neutral observers and advocates of further research and development. Some small-scale initiatives from that period are still trying to enable hydrogen-fueled land transport. However, this application faces many issues, given fundamentally low conversion efficiencies and competition from other sources. Rationale. A hydrogen economy was proposed by the University of Michigan to solve some of the negative effects of using hydrocarbon fuels where the carbon is released to the atmosphere. Modern interest in the hydrogen economy can generally be traced to a 1970 technical report by Lawrence W. Jones of the University of Michigan. In the current hydrocarbon economy, transportation is fueled primarily by petroleum. Burning of hydrocarbon fuels emits carbon dioxide and other pollutants. The supply of economically usable hydrocarbon resources in the world is limited, and the demand for hydrocarbon fuels is increasing, particularly in China, India, and other developing countries. Proponents of a world-scale hydrogen economy argue that hydrogen can be an environmentally cleaner source of energy to end users, particularly in transportation applications, without release of pollutants or carbon dioxide at the point of end use. A 2004 analysis asserted that most of the hydrogen supply chain pathways would release significantly less carbon dioxide into the atmosphere than would gasoline used in hybrid electric vehicles, and that significant reductions in carbon dioxide emissions would be possible if carbon capture or carbon sequestration methods were utilized at the site of energy or hydrogen production. Hydrogen has a high energy density by weight but has a low energy density by volume when not highly compressed or liquefied. An Otto-cycle internal combustion engine running on hydrogen is said to have a maximum efficiency of about 38%, 8% higher than a gasoline internal combustion engine. The combination of the fuel cell and electric motor is 2 to 3 times more efficient than an internal combustion engine. However, the high capital costs of fuel cells, about $5,500 per kW in 2002, are one of the major obstacles of its development, meaning that the fuel cell is only technically, but not economically, more efficient than an internal combustion engine. Other technical obstacles include hydrogen storage issues and the purity requirement of hydrogen used in fuel cells. With current technology, an operating fuel cell requires the purity of hydrogen to be as high as 99.999%. On the other hand, hydrogen engine conversion technology is more economical than fuel cells. Current hydrogen market. Hydrogen production is a large and growing industry. Globally, some 57 million metric tons of hydrogen, equal to about 170 million tons of oil equivalent, were produced in 2004. The growth rate is around 10% per year. Within the United States, 2004 production was about 11 million metric tons, an average power flow of 48 gigawatts. As of 2005, the economic value of all hydrogen produced worldwide is about $135 billion per year. There are two primary uses for hydrogen today. About half is used in the Haber process to produce ammonia, which is then used directly or indirectly as fertilizer. Because both the world population and the intensive agriculture used to support it are growing, ammonia demand is growing. The other half of current hydrogen production is used to convert heavy petroleum sources into lighter fractions suitable for use as fuels. This latter process is known as hydrocracking. Hydrocracking represents an even larger growth area, since rising oil prices encourage oil companies to extract poorer source material, such as tar sands and oil shale. The scale economies inherent in large-scale oil refining and fertilizer manufacture make possible on-site production and captive use. Smaller quantities of merchant hydrogen are manufactured and delivered to end users as well. If energy for hydrogen production were available, use of the substance for hydrocarbon synfuel production could expand captive use of hydrogen by a factor of 5 to 10. Present U.S. use of hydrogen for hydrocracking is roughly 4 mount per year. It is estimated that 37.7 mount year of hydrogen would be sufficient to convert enough domestic coal to liquid fuels to end U.S. dependence on foreign oil importation, and less than half this figure to end dependence on Middle East oil. Coal liquefaction would present significantly worse emissions of carbon dioxide than does the current system of burning fossil petroleum, but it would eliminate the political and economic vulnerabilities inherent in oil importation. Currently, global hydrogen production is 48% from natural gas, 30% from oil, and 18% from coal. Water electrolysis accounts for only 4%. The distribution of production reflects the effects of thermodynamic constraints on economic choices. Of the 4 methods for obtaining hydrogen, partial combustion of natural gas in a NGCC power plant offers the most efficient chemical pathway and the greatest offtake of usable heat energy. The large market and sharply rising prices in fossil fuels have also stimulated great interest in alternate, cheaper means of hydrogen production. As of 2002, most hydrogen is produced on-site and the cost is approximately 70 cents per kilogram if not produced on-site. The cost of liquid hydrogen is about $2.20 per kilogram to $3.08 per kilogram.